Hello and welcome back to Calculus 3. This is the second lecture. It's 15 feet of snow outside, so another YouTube lecture. And this is going to be about tangent planes and linear approximation. Before we dive into the tangent plane, we are going to talk about tangent line. The purpose is going to be the same. We're just going to move from tangent lines into tangent planes. Let's first take a look at Calc 1 and see what was important for tangent planes. So tangent lines. So tangent line. Well, we had xy coordinate system, xy plane, and then we had some function in that system, f of x, and then we said, I want to measure the change at some point. So we pick a point, let's say right here, and then let's call that at A, and then we can find a tangent line. Let's use purple because of the request. I have tangent line, call that tangent line T. So what am I going to do now? Well, I am going to first compute the slope of that tangent line by finding the derivative of f and computing it at A. And then I am going to compute the y value by computing f of A. And then I'm going to use, we can use point slope formula, so y minus y1 is equal to mx minus x1, right? And have y minus, well, in this case f of A is equal to f prime of A x minus A, because my x1 xy y1 is A f of A. That's the point at which we are computing. So I am able to find the equation of the tangent line by simply computing this expression and then add f of A. Actually, in general, people put f of A in front, so let's do that here. F of A plus f prime of A times x minus A. So this was the tangent line in Calculus 1, and what it measured is, because it has a slope, right? It measures the change, the instantaneous change at the point. Now, observe that the tangent line is a 2D line and it cuts the space of xy in two parts. When you draw that line, it cuts because the line goes to infinity to both sides, so it cuts the entire space R2 into two parts. Now, so what would be the analogous thing in the 3D world that you can use to cut the entire 3D space into two parts? Well, clearly you cannot use the line because you can just go around the line, right? So you have to use a plane. And you think of the wall. So if the wall is to extend indefinitely in all directions, the wall would split all of the R3 space, which is the entire universe we are in, into two parts. So now we are jumping from the two-dimensional Calculus 1 into Calculus 3, where if we have some kind of a three-dimensional shape, and you have a point somewhere on the surface, you will draw a tangent plane that will contain that point. By the way, when you're graduating, make sure that you point that out, those graduation hats you have, it's actually just a tangent plane to your head. That's all it is. So what we have now is we have this point of interest here, and that point is going to be AB and then f of AB, because you are computing the z value when you plug in A and B into the function, which is the surface that you have. And you also know, hopefully, from before, that you have the equation for the plane to be ax minus x0 plus b y minus y0 plus c z minus z0 equal 0. So that was the equation for the plane. Equation of the plane. So now what am I going to do? I can put all of this together. The only issue is that I really don't know what A, B, and C is, because earlier we had the normal vector, right? So the normal vector was the one that was, you know, the air quotes around carrier of the slope of the steepness of the plane, and that vector is always perpendicular to the surface of the always orthogonal to the surface. So now what I'm going to do is I'm going to define that vector, which we used to call vector n, that was ABC. Now that vector is going to be our del f at ABC. So that's what we're going to do. We are going to take the del f, and oh, we have ABC and ABC. I don't like this. I don't like this. Hold on. Because the point is AB, these are AB components of a vector, so I'll have to rename these to maybe N1, N2, N3. So those are my N1, N2, N3 from our first lecture when we learned about planes for the first time. And now I'm going to replace those by the del of f, which is just our the vector of partial derivatives. So what is our normal vector now? Oh, come on, pen, work. Hold on, my pen stopped working. There we go. So what is the normal vector now for our tangent plane? Normal vector is going to be partial derivative of x computed at AB, and then partial derivative of y computed at AB. So that's our normal vector, is just going to be the del of all of these guys. And what do I have for, oh, hold on, ABC. We have the C component there. Perfect. Nice. All right. So now what I'm going to do is I'm going to create the vector equation of the tangent plane. So let's write this. This is the important bit. So equation of the tangent plane. Equation of the tangent plane is, what do I have? I have all the partial derivatives, right? So it's going to be partial derivative of, in respect to x, computed at ABC times x minus a, plus partial derivative of y computed at ABC times y minus b, plus partial derivative in respect to z ABC times z minus c equal to 0. Barely fit. All right, there we go. So this is our equation for the tangent plane. And if you just simply look at this, you have your partial derivatives computed at, so partial derivatives computed at the point of interest, and then the rest of the stuff, x minus a, y minus b, and z minus c, is the standard what you had from your previous calculations you did for the tangent plane, just for the plane, right? So let's take a look at our previous example. So let's say we have the surface, which is actually f of xy, right? Z equals f of xy, given as, again, some of those paraboloid's easy to deal with. Say we have whatever we had, 10 minus, if I can't remember, but let's say, I believe this was it, 10 minus x squared minus, and we want to do, we want to find the tangent point at the tangent plane at the point in a domain. Let's say it was 1, 3, I remember. So we can actually figure out what the z value is by plugging in 1 and 3 in the original problem and just computing everything. So let's figure things out. The first part is to find the z coordinate of the point, because this is clearly just the part in the domain. Remember, I'll go back to Calculus 1. You are looking for the tangent line at A. Line is two-dimensional. At A, that's just one point. So you have your input is just given for the point from the domain. You are still going to go one dimension higher and compute what you need, which is done here. You compute your y to have a which is x comma y for a point, and then use together with a slope. So again, now our domain is two-dimensional. It's x and a y. But see, we didn't get z, but we need z for our calculation, which is going to be the c, right? That's what we need. So these two guys over here are a and b. I still need that c. So what's c? C is going to be z when you compute function at 1 and 3. So what do you have? You have 10 minus 1 squared minus 3 times 3 squared. That's going to be 9 minus 27, which is negative 18, I hope. So let's see, 10 minus 1 squared, that's a 1, so that's 9. And then minus 3 times 9, 27. Yep, that's good. So now I have my point as 1, 3, negative 18. And I'm just going to put equal because this is your ABC. Okay. Now we need to figure out all of the partial derivatives so that we can find the normal vector. Okay, so that's going to be fx. First off, you will need fx, fy, and fz. So what I'm going to do is I'm going to take this z and move it to the other side of the equation and have everything equal to 0. So my original equation is z equals 10 minus x squared minus 3y squared. And I'm going to just move z to the other side. That gives me 10 minus x squared minus 3y squared minus z equal to 0. You can put 0 in front or in the back, it doesn't matter. So now let's go. What's fx? Fx of xy and z. Well, fx of xy and z is just simply negative 2x. Fy, which is the partial derivative in respect to y, of this is going to be negative 6y, and fz is going to be xy, z, and then that's negative 1 when you take the derivative. Now, I need to compute each one of those at ABC, but I have ABC, that's my 1, 3, and negative 18. So fx computed at 1, 3, negative 18 is simply negative 2. Fy computed at 1, 3, negative 18 is, when you plug in 18, great. So 18 times 3, 48, also 96. So, and no, it's just 3, sorry. Negative 6 times 3 is negative 18, good. And then fz of 1, 3, negative 18, well, that's just negative 1, because there's nothing to plug in any of the other numbers. So what do I have now? I just have, this is my vector n from good old days of making planes. Negative 2, negative 18, and negative 1. Great. Let's make the plane. So what's the tangent plane? It's given by negative 2, x minus, and our point is 1, 3, so minus 1, minus 18 times y minus 3, minus 1 times z minus 18, equals to 0. Now, what we can do is we can multiply everywhere by -1 and just make this nicer, right? So -1 will make all of these positive, and then you just need to distribute. So you have 2x minus 2 plus 18y minus 54. And this is positive in front again because of the -1 over there. We just have plus z minus 18 equal to 0 for the total of 2x plus 18y plus single z is equal to, what do I have? I have all of these and they're all negative. It's -74, so positive 74 on the right hand side, and that is the tangent plane at that point 1, 3, 18. I mean 1, 3, -18. So that's the tangent plane. Clearly, as soon as you change the location where you want to look for the tangent plane, the entire calculation changes because you will have different fx, fy, fz. Now, notation-wise, when you are looking in the book, there is this notion of implicit and explicit function. So if I write z equals 10 minus x squared minus 3y squared, this is known as explicit. Because I was able to say z equals everything else, like y equals x squared or y equals sine x, any of those from your calculus, pre-calculus 3 era functions. But now you also have what we call implicit form of a function when you put all of the variables on one side, whether they are independent, dependent, whatever they are, just put all of that stuff on the left and then have it equal to 0. So if I have 10 minus x squared minus 3y squared minus z equals 0, this will be known as implicit function. Now, the notation for the one on top would be lowercase z, lowercase f, and so on. And the one on the bottom is capital F. So if you look at your formula in a textbook, they don't actually say fx like I said fx. They said capital Fx of ABC. And the reason why they use capital is because you actually find those partial derivatives from the implicit form. So we are going to actually, this function here is going to be some function of x and y and z, which is equal to 0. And that is implicit form. So we have explicit form and implicit form for functions. So that's where the capital F is coming from in the notation that it's presented in the book, just in case you are not sure. So the first order of business is to make the function equal to actually here let's write it this way. So z is equal to f of x y, and that is equal to 10 minus x squared minus 3y squared. Capital F of x, y, z is equal to, and you have 10 minus x squared minus 3y squared minus z equal to 0. All right, so these two are same, but they're different notation. They're different notation. One is given as explicit function, the other one is given as implicit function, but they do the same thing. I mean, they trace the same object. So what do we do with this? Well, sure, you have the tangent plane, and you know how steep the space is around, right on that plane, how steep the space is around the point that you are looking at. But then, can we do more with this, right? What else can we achieve? Well, we can deal with a linear approximation, just like we dealt with the linear approximation in Calculus 1. Now, it's true that we have power of computers today to compute technically anything. I will give you the reasoning behind doing this by hand in the good old days, but I really don't have reasoning for doing it now. So we're back to Calc 1 now. We are talking about linear approximation, right? So back to Calculus 1. What do I have? I have, let's say I want to compute square root of 10. Right? Square root of 10 is how much? Right? So what do I know? Well, I know how to compute square root of 9. That's equal to 3, right? And the reasoning goes like this. If I have a graph of a function, and this is where my 10 is, and I don't know what the value for that is. But then there is also 9 in front, which is here, that has 9,3, something that it's very easy to solve. So that's what 9 is, right? All the other numbers in between, obviously, before. So this is my elevation 3, exactly 3. And this is for 10, something more. We don't know how much. Well, we can approximate that value, because if you draw the tangent line, let me actually use the tangent line different color here, purple again, I guess. So you draw the tangent line. It's very difficult to see that the y value of the tangent line and the y value of what you want to compute are apart on this sloppy drawing. But these points are very, very close. So it's good enough for us to find the tangent line at the point that it's easy to compute, in our case 9, and then compute 10 in that tangent line, because again, the tangent line is going to have a y value for x equals 10. So what do I do real quick? I find the tangent line for this at 9. That's what I find the tangent line. So we have that the point A is 9. That's what I have. Point A is 9. And then I have to take my derivatives. Now, if you recall the formula I wrote before, it was f of A plus the derivative of A times x minus A. And we know A is 9. So that's y equals f of 9 is the square root of 9 plus the derivative of the square root is 1 over 2 times root 9. And then you have x minus 9. So that's, we plugged everything in. The derivative of square root of x, which is the function that we are observing, is 1 over 2 root x. That's probably the only thing that might be tripping you now. So this is 1 over 6 times x minus 9. And we can simplify this into 3 plus 1 over 6x minus 9 over 6. Well, that cancels to 3 halves, right? So if that's 3 halves, and I have 3, so 3 minus 3 halves is 3 halves. Great. So I have my tangent line as y equals 1 over 6x plus 3 halves. And this is the tangent line at x equals to 9. And we use that line to compute 10. So square root of 10 is approximately equal to the 1 over 6 times 10 plus 3 halves. So I'm, instead of computing the exact y value for square root of 10, I'm going to compute number 10 in the tangent line, because the y value of the tangent line, we're looking at this point here, y coordinate of the tangent line is very close, it's almost the same as the y value of what you actually wanted to compute, which is root 10. So now what do I have? I have 10 over 6. When you cancel that, you get 5/3 plus 3 halves. The common denominator, should have left it as 6 and just find the common denominator. Yeah, let's do that. So times 3 times 3, forget about this stuff. It's going to be common denominator 6. 10 plus 9 is going to be 19 over 6, which is 18 divided by 6 is 3, so this is 3 point, and then you have 1 as leftover, so it's 1 over 6. So actually, I could use the calculator to get, well, 1/6 is 1.666 going forever. Now, what I want to do here is I want to say that the square root of 10 is approximated to be 3.166, right, going on forever. So that's that. What I want to do is I actually want to compute square root of 10 and see what the actual value of square root of 10 is. So let me just get the abacus going. There we go. So square root of 10 on the calculator. So square root of 10 approximated by a calculator is 3.162223. Look at that. So we are 4 thousandths off. 4 thousandths off. That's not a big deal at all, right? And we computed everything by hand. So that was the reasoning for us. Now, again, calculators are about 50 years old. So this linear approximation that we learned in Calculus 1 was the way to compute all of the values that we needed at the time. Now you have calculators, so you can just be brain dead all the time. We are going to move this now into Calculus 3 and use it the same exact way. I want you to think about your graduation hat, right? Think of your graduation hat and understand that that thing is the tangent plane. So that thing is the tangent plane, right? This is the part that you put on your head. It will go like that, right? So this graduation hat is the tangent plane to the surface of your head. You know, you can tilt it on the side, you can, you know, pull forward, backward, whatever, you put it normal. Then no matter where you position it, it's going to be a tangent to your head. Now, there is only one point that it's actually touching your head, let's say, and that's the point that I have in the middle on this drawing. Now, that was the point at which it was easy for us to set up the tangent plane. And now, if you are interested in some reasonable neighborhood around the point, if you are interested in computing the z value in this case, well, clearly you can use the tangent plane rather than using the calculator to do this thing. So let's find the linear approximation question in the homework section and work the way through. So linear approximation, let's see something interesting like problem, 29 has ln. So, all right, so I'm going to leave the graduation hat that's the graduation hat, and then I'll just say this is a tangent plane actually. All right, let's take a look at 29. So it says linear approximation, so we can compute the stuff. So what do they want? They say here f of xy. So they give us f of xy, and that f of xy is ln of 1 plus x plus y. And they want to compute f of 0.1 and negative 0.2. Right, so that's the goal. We are actually going to do the same thing we did in Calculus 1. We are going to find the tangent plane, and then we are going to compute at the values that we want. So what are the values that we should actually use to compute this? What is AB? Well, AB is clearly 0, 0 in this case, because both of these numbers that are given are very close to number 0, and 0 is easy to compute in every aspect of this life. So what do I have from Calc 1? If you recall, in Calc 1, I'm going to erase this. In Calculus 1, we said that the linear approximation y was f computed at a plus the derivative computed at a times x minus a. Now I need to go and make this 3D, need to move this to the z level. So if this is z, then this guy over here must be f of a, b, plus this better be the partial derivative computed at a, b times x minus a. And then we also need the other one, which is f of y, computed at a, b, with y minus b. So this over here, now I'm going to erase. First, before I erase it, please look at the corresponding terms and realize that this is the same deal we had in Calculus 1. We're just going to extend the extra term for y direction over there. You can build this for 10D if you want to from what you see right now. So what I'm going to do is I'm going to get all of these. So I'm going to get rid of the Calculus 1 part, and I'm going to heavy box this here, say equation of the tangent plane. So what do I do? Well, I need all of these components, right? So what's the plane? Plane is z equals function computed at AB, or function computed at 0, 0. That's just ln1, right? Plus the partial derivative in respect to x. Okay. Partial derivative in respect to x, this is ln, so the entire, you know what, let me just find partial derivatives first. So fx is ln, you do the division, you write the argument as is on the bottom, and then its derivative on top, which is just 1. And then we also need fy. Now that's symmetric, so it's going to look the same. There we go. Now, what do I need? Well, I have z equals, and I'm computing ln at 0, 0, so it's just ln1, plus I'm computing the derivative at 0, 0, well, that's 1, times x minus 0, right? Because a is 0. And then plus y, it's also 1, times y minus 0. So what do I get? ln of 1 is 0, so I have z equals x plus y. What is the equation of the tangent plane? It's x plus y minus z equals 0. And that's the equation of the tangent plane. TP, tangent plane. Now that's tangent plane at 0, 0. Now, what do they want? They want us to compute the point 0, 1, negative 0, 2. So what is the z? Sorry, what is f of 0.1, negative 0.2? Well, it is approximately the same as computing this, which is 0.1 plus negative 0.2, which is negative 0.1. That's what it is. Now, how do we check this? Well, since we have a calculator, we can actually compute f at 0.1, negative 0.2, because that's just going to be ln of 1 plus 0.1 minus 0.2. So you are technically looking for ln at 0.9. And you can use your calculator to figure that value. So what is the ln of 0.1? Well, ln 0.9 is going to be approximated as negative 0.1 0.05. We got exactly negative 0.1, and the check and the exact calculation is negative, well, the exact decimals go forever, is negative 0.105. So you see that it's extremely precise, it's really good. Now, everything you see that it's written on this current page, screen, whatever you want to call it, is actually to replace the last line, because, as I said, if we don't have the calculator, what is really ln of 0.9, right? You don't get to compute that to be negative 0.105 without the calculator. So the entire procedure up there is the procedure that, let's say the calculators don't exist, let's say even if they do, you don't have the batteries, right, and so on. So that's the linear approximation part. You will look at the closest location that you can easily compute. You will compute the tangent plane at that location, and once you have the tangent plane, you are going to compute the point that they actually want in the tangent plane because it's close enough. And that's the part on linear approximation. The last part of this lecture is on differential. Again, going back to Calc 1, talk about differential. It was a simple mathematical manipulation between Newton notation and Leibniz notation, right? So what we do is we first write y is equal to f of x, which is the pre-calculus part, and then we take the derivative of the whole thing, and we have dy dx, which is Leibniz notation, is equal to f prime of x, which is approximately Newton's notation. Newton had y with a dot on top, so that dot migrated into a prime and then eventually f prime, right? So it's a progression in notation. Anyway, so we have this, and then you have your dy is equal to f prime of x dx, and you have your differential formula. Now, what is important to know on a side is that delta x is x2 minus x1. This is change in x. And we need to know that dx and delta x are the same thing. Now, delta y, which is y2 minus y1, is change in y. And it's important to know that the dy is approximately equal to d delta y. That's the key point. So, what does the linear approximation do? Linear approximation approximates the value. Differentials approximate the change. So not the value itself, but the change when you go from value 1 to value 2. So now, can I compute square root of 10 using differentials? And the answer is yes, because I know that f of x is root x, right? I see the shape of what I'm looking for. Is it ln 10? Is it square root of 10? What am I looking for? Sine of 10, right? So I have the function just by looking at the form of what they want. Now, once I have that, I need the derivative. And we know that the derivative is 1 over 2 root x. And I also need a is equal to 9, the closest point that I can actually compute. Now, here is the cool part. You want to have a change from 9 to 10, because you are, right? So you are calculating delta x, right, as 9 minus 10, and you are getting negative 1. So the change of x is a negative 1. You are going from 9 to 10. So the change is negative 1. So I have all of the pieces now. The dy is equal to f prime computed at a times dx, but we also know that f prime at a, dx and delta x are the same thing. So that's technically my formula. So the actual, oh no, I don't need that. The actual change of y is approximately equal to dy, which is equal to the derivative computed at 9, so that's 1 over 2 root 9, times the change, which is negative 1. Now this whole thing over here is 1 over 6, so negative 1 over 6. And that's the change in y. So oh, hold on. I think I put this backwards. Because, yeah. So what is square root of 10? I think I'll have to fix this. Square root of 10 is the square root of 9 plus the change. Yeah, I have it backwards. This is supposed to be 10 minus 9, which gives me positive 1. And that gives me positive 1 over here, which gives me positive value, because I need to add 1 over 6 to it. There we go. So that's 3 plus 1 over 6, and we get our 3.1666 we had before. So what we did is we approximated the change when you go from one value to another, and then we added that to the value that we can compute to get approximation for the one that we can't compute without the calculator. So linear approximation here in blood so linear approximation approximates the value. We got here this directly, where the differentials approximate the change. So what I did is I calculated the change, which is 1 over 6, and then I used that to... So now, what do we do with Calc 3? Well, same thing, except you have one more term. You are going to write that the differential. Let's put now title. Yeah. Differentials in R3, right? Three-dimensional differential. So what do I have? You have delta z, right, is approximated by dz, and that one is equal to fxab times the change in x plus fyab times the change in y. And as you can see, it's the same formula like in Calc 1. Except now you have to have two partial derivatives because you have those two main directions. So let's take a look at an example of this. Now most of these examples should be word problems because that's what we use it for. Let's see. Travel cost. Cost of a trip that it's L miles long. Driving a car that gets M miles per gallon with the gas costs of P dollars per gallon is given. Okay, so this is a problem. This is problem 44, and it's applied problem, which is great. So what do I have? I have the cost to be LP divided by M. So you're planning a trip that it's 1,500 miles. and the car gets 32 miles per gallon with the gas cost of P equals $3.80 per gallon. So that's the cost. So what do I need? What do I want to consider? Say, estimate the change in the total cost of the trip. So we are looking for the change in the cost of the trip. If you drive extra 20 miles, so if L, which is planned to be 1500, goes to 1520, and miles per gallon by some miracle go from 32 miles per gallon to 31 miles per. Oh no, it's not by miracle. This is actually good because, yeah, the more you drive the car, the less efficient it gets. So yeah, and the price of the gas changes from 380 to 385. So which way? So we're going to drive more miles. We are going to drive, our car efficiency is going to be worse, and the price of gas increases. So how much would that change the cost? We can actually compute the exact value easily, but let's have fun using calculus, and I'll explain the rest as we go along. So what do I have? I have 4 variables. Cost depends on 3 variables: length of the trip, price of the gas, and gas mileage of the car. So this means that the change in cost will be approximated with the change with the DC, right, which is equal to, and now I need the differential for this. So it's going to be the cost function taking derivative in respect to L, computed at these points. We can call them ABC, right? So ABC, there we go. Times the change in the length of the road trip, plus cost as a partial derivative of gas price computed at ABC, times the change in the gas price. And finally, plus the cost as a derivative of gas mileage computed at ABC, times the change in gas mileage. So we created the formula for the approximation of the change, and now I need to compute all of the little pieces. So first off, I have my my ABC, right? I have my ABC set as 1500. Then we deal with the price, right? So P, that will be 380 and 32. So this is the base state, and then I have the change in. I'm not sure why I'm calling it ABC when I can just call it LP. Yeah, I can just call it LPM, which is what it is. LPM over here. LPM. LPM. And LPM. So change in L is 20. Change in P is 0.05. And change in gas mileage is -1. It got worse. I also need partial derivatives. So C L, partial derivative, in respect to L. So if L is the variable, we are looking at the function. I'm going to write the function down. So LP over M. So if L is the variable, then it's just P over M. If P is the variable, then it's just L over M. And if M is the variable, well, then we have a derivative to take, which is negative LP divided by M squared. That's the partial derivative in respect to M. It's like taking the derivative of 1 over x. What's the derivative of 1 over x? It's negative 1 over x squared. So that's that part and that negative there. LP is a constant that you just multiply. So yeah, there. So I have those. And now I can approximate the change in cost by simply computing the cost differential. So that's going to be CL. So that's the derivative computed at PM. So I'm just going to write this. So PM times delta L plus LM times delta P plus negative LP over M squared times, oh, this is supposed to be change in P and change in M. So all I need to do now is to plug everything in. So the cost is approximated by P. We said that P is 380 divided by M, which is 32, times the change in L, which is 20, plus L over M. So L is 1500 divided by M, which is 32, times the change in price, which is 0.05, plus, actually I could do minus, 1500 times P, which is 3.80, divided by M, which is 32 squared, times the change in M, which is negative 1. And now we just need to compute all of this mess. Okay, so let me just get the calculator to go through this quickly, so we don't stay all night. There are snowmen to be made, right? Is it dark outside yet? Should be. I don't know. What's the time? Oh, 7:17. Good. All right. So we have 3.8 times 20 divided by 32, and that gives us 2.375 plus 2 zeros cancel, so 15 times 5 divided by 32 gives us 2.34. Actually, I should just keep cents because this is cents, it's cost. And then we have plus because of the negative 1 over there. I have 15 times 38. No. Times 3.8 divided by 32 squared is 5.57. So the change in cost is approximately 2.38 plus 2.34 plus 5.57 to give us about $10.29 in the cost difference. So all of the features, and we see that from the analysis we see that the price of the trip should be worse because all of the components that we did for the change were against us. You're going extra 20 miles. Your price of the gas is extra 5 cents per gallon. And your efficiency of the car is down by 1 mile per gallon because, I don't know, you got tired. So these are all of the calculations, and you see that you can approximate. Now, can you find the exact? And the answer is yes. You can use the formula that it's given, right? Because this one is cheap. This is obviously used for something that is far more complicated to compute. You can compute the actual numbers here, and then you can compute the changed numbers in there and just subtract the two, right? And you will get. So I want to actually do that and see how well our approximation held up. So if I have the original state, the planned situation, which is 1500 times price of the gas is $3.80 divided by 32 miles per gallon, we are looking at the cost of the trip to be $178.13. Now I redo the same calculation with new numbers. So that's 1520 times 3.85 divided by 31, and we get for the moment I typed something wrong. The number that I got was nothing. So it's 188.77. So if you take a look at this, the difference is 10.64. So that will be exact. That's the exact cost, the exact difference. If you use the old numbers, use the new numbers, you do the difference between the two, and you have the exact difference. So it's 10.64. We got, with our calculation, 10.29. That's pretty good. Now, again, it's much easier to do what I just did than everything else. But again, this is used for much tougher situations, again, when calculators are not available and all of these things. So, you know, right now there is not a great need for all of us to be involved in such calculations because computers and software does these calculations for us, and no matter what we assign, it will be calculated. So that's the entire lecture. You have tangent planes, linear approximation using tangent planes, and then you have the differentials, which approximate the change. So we will now go to our break, and then after the break we are going to when we meet Monday after the spring break, we are going to do a few of these examples to refresh all of this, and then go on and do the next lecture. So only one lecture on 12.8 for class prep, and then obviously whatever you missed for class preps up to that point. I will see you all in about 10 days or so. Bye.